All right, so the next thing that we're going to talk about is, sorry, I'm moving back and forth, is chunking. So this has come up a couple times, and I've kind of sidestepped the issue, so now's the time to talk about it. This is a feature that doesn't have an analogy in NumPy at all, but is something that's incredibly useful, and it's a core feature of HDF5. So we're going to really get into how this works. So chunking, more or less, is the ability that you have to break up your array into multiple discrete blocks that you then reason about. So those blocks have to be of equal or lesser rank and equal or lesser size for obvious reasons, right? You can't have a chunk that's bigger than your actual array size. However, that's specified. So what ends up happening when you have these chunks is that there's metadata that you don't have access to, but there's basically a B tree that stores where all of the chunks on disk are and what the indices into those chunks are, because that's how a B tree works. So every data space is comprised of chunks. The chunk is basically the smallest unit of information that HDF5 will reason about. Everything is a chunk. So arrays are chunks, tables are chunks, etc. So this is one of the core abstractions of HDF5, and all operations happen on the chunk level, reading, writing, compression, etc. So chunking is really useful because it allows you to store sparse data ridiculously efficiently. You can, if your chunk size is 1, which entails some overhead on your B tree, obviously, that might be okay, depending on the sparsity of your matrix, right? Because you're only going to store the chunks where you have real data, and chunks where there isn't data, you're going to skip over. They don't actually need to exist on disk. And you could assume that those are 0. This also allows you to have infinitely variable length data sets and infinite data sets. So because you've got this notion of a chunk somewhere in memory, or somewhere on disk, excuse me, you can append to that array, unlike in NumPy, just by adding another chunk, right, at the next lower index. And you can keep adding, right? And you can do that in multiple different dimensions. So that's how you get these extendable arrays, and that's also how you get infinite arrays, right? Because you can just say, I don't care what the maximum dimension size is. Like, it can just go on forever. Now, in practice, obviously, you're limited by how much disk space you have, but you can just keep going on forever. In HDF5, the B tree implementation will handle that. So, and there's some cool tricks there that if you end up with more indices than can be stored in a 64-bit float or 64-bit int, you go to like sub B trees and it gets stored automatically. So this really is like, there's nesting there that happens. It is effectively infinite. You're not even limited by 64-bit integers. So chunking's awesome. So as I mentioned before, PyTables only allows you to extend infinitely in one dimension. That's because PyTables, as the name would imply, is sort of conceived around this tables notion, less than conceived around the notion of an array. But if you need multiple extendable arrays, go to H5Py for the time being. Although pull requests welcome. This is shamelessly stolen from the HDF5 documentation because I didn't want to remake these figures. But the basic idea is your data set consists of some metadata, or here in this figure, your header information, which includes the B tree. Um, and some contiguous block of data, right? So if, or some block of data. So in a naive implementation of a database, you would just say, okay, well, I've got this array, it's this length. I'm just going to stick all the bytes right next to each other, and that's going to be how it works. HDF5 does not work like that unless you only have one chunk. Instead, what HDF5 does is every chunk gets stored in a separate part of the file, which it keeps a reference to and dereferences automatically. So you've got your array, even though you're going to think about it as this contiguous chunk of memory. In fact, it's not a contiguous chunk of memory on disk. It's broken up by whatever your chunk shape is. Okay? Does that make sense to people? Yeah? Okay. So here's a couple important things. All input-output happens on the chunk level. So you can never read less than the size of a chunk. Even if you go to only access one element, you're going to get the full chunk. Now, most of that will be discarded for you when you access one element, depending on your chunk size. But you're only going to get that chunk. So the edges of your chunk may extend beyond what your real data set is, as long as you have where you have real data, as long as you're in that in a chunked data set, right? You're not fixing your size, and it's still within the bounds. If that happens, those locations where you don't have data that you're trying to read from or write to are going to get filled in with a default value. Now that default value is user specifiable. You may have noticed back several slides in the descriptions. Maybe we can just go there temporarily. The descriptions of some of these tables in the atoms will have, or in the atomic types, yeah, there's a lot of slides. Sorry. They'll have a default value. And most of the time for numeric types, that's 0, like you would expect. It does not have to be 0. It can be whatever you want. That is an HDF5 feature, not a PyTables one. So if you wanted your default value to be 42, it could be 42. Okay. Time to skip several through the whole presentation. Okay. One of the things that this allows is reading and writing in parallel. Because all chunks are independent, you can read chunks independently. So that's really useful if you want to do higher throughput I/O. And this is one of the things that MPI does for you. PyTables does it for you in a different way, but it's the same idea. Like you just go to a different point on disk, and you can read from there. So picking your chunk size is actually somewhat, and your chunk shape is somewhat of a fine art, and will impact the performance of your code fairly significantly. So if you're looking to access only small amounts of data at a time, smaller chunk sizes are better, right? For obvious reasons. You're not reading in all this extra data just to throw it away. If you're going to access lots of data simultaneously, then bigger chunk sizes are better. Another thing that affects chunk size is the data type, right? So if you've got some complex data type, or you've got, or is the number of elements that you might pull out simultaneously is going to be fewer than if you have a simpler data type with less data. And really what's affected here is how much data can you store in L1, L2, and memory, right? And if in the best situation, you want to try to keep it so that the chunk size is roughly equivalent to L1 cache or half of L1 cache, depending on like the performance of your system. And in those cases, you get a definite speed boost because any operation that you do on that data is going to be done in this. The data is all right going to be there on the processor already. So, yeah. No. So, yeah. So the question was, is PyTables safe for writing across multiple processes? And the answer is no. You can read from multiple processes safely, but writing from PyTables is not. If you want to write, you have to. If you want to write in parallel, you should use MPI, which currently is only available in H5Py from the Python layer. So, yeah. I mean that. And MPI is how they get to these really ridiculously large data sets where you're in the petabytes or exabyte kind of territory. So, yeah. Okay. Typically, if you do that, if you want to write to multiple processes, what I do is I linearize it. So I have one write process, and you just push the data to that write process, and it batches it and takes care of it. And I've never had a problem even up to the sort of gigabyte, terabyte scale doing that. If your data is much bigger than that, then you really should consider MPI. So, okay. Yeah, any questions on these points here? So the hyperslab is basically is your indexing operations that follow NumPy. That creates your hyperslabs for you. Yeah. Yep. Yep. And you don't read in the intermediate chunks and all that nice stuff. So, yep. Yeah. So I use multi-processing pools for that. So I would take one process and be like, and say you're the right process. And so at that point, it's all in memory still, right? So you send your NumPy array back and forth if you need to, yeah. Or you just have your write process be your main process. So whatever you have some compute pool, and then you return data to from your multi-process pool, and then write it out. Yeah, it can get a little hairy if you do it wrong, but the main idea there is to just only have one thing writing. So, yeah, but you can open up as many read processes as you want as long as the file handle itself is opened read-only mode in the process that's reading it. If you try to share the file handle, sometimes you get into weird situations too, obviously. You don't need to. That's just like if you go, so say you've got some chunked sparse matrix or array, and you've got, points. Sorry, I'll just draw this. We'll get to an example here soon. But if you got some array and this is filled, and you've got some like diagonal elements filled, and then you go to read in this element. That element doesn't exist, or these elements don't exist on disk. So what you'll get is the default values. You'll get an array of the default values for that area, for that region. Does that make sense?
Yeah, so it takes up space.
No, it doesn't take up space. It'll take up space in memory, but not on disk. Yeah. No, it won't tell you. This is. I mean, yeah, it's not safe in any way. Like, for lack of a better term, this is like, you told me to do this. This was the state that I was in. Like, if you want safety, you have to write the safety yourself. So, yeah. Safety gets in the way of like very parallel jobs. So that's why. What? Yeah, right, exactly. Yeah. Uh-huh. Uh-huh.
chunks or, like
Yeah, so the question is if you have a large CSV file, can you do that directly rather than creating an NumPy array or do it in chunks or whatever? So the answer is yes to all of those. So yes, you can create it without a NumPy array. You can just create it as like a list of tuples or something. Like as long as you have the appropriate description. And the descriptions don't have to be D types. You can use other description formats which you can look up on the PyTables website. Although I don't recommend it. And again, like I would just, what I would do in that case if I wanted it to be chunked, I would create the data type, create a NumPy array for just like, n rows, like the first 100 rows and the second 100 rows or whatever, and go through and do a write operation for each one of those. For CSV files in specific, in more recent times, if it's well formed and everything, what I would do is I would just load it into pandas, and then pandas has an HDF5 output data store that is backed by PyTables. So it uses PyTables under the covers. So you would just get it into a pandas data frame from the CSV file and then write it out to HDF5, and it would do all of this magic for you. So it's pretty cool. That's what I would do these days. Yeah, I imagine that you can. So. No, so chunk shape is specified just as it's a tuple. It's the same thing as the shape. So a NumPy shape is a tuple of ints. Chunk shape is the same thing, similar meaning. So, does that make sense? So the item size will change based on the data type, right? But the chunk shape. So the PyTables will try to compute an optimal chunk shape if you don't provide it, and that optimal one, so the default, like whatever you get just out of the box, will change based on like these kind of hand-wavy heuristics about what your optimal size is based on the item size, and your processor speed and all that stuff. So, yeah. Sorry. Okay. Any other questions? How fast is the creation of the files? What do you mean? So in general, it's much faster because you're storing a lot less data. Yeah, that goes back to this like thing that we described at the very beginning, where the strings in general are going to be a lot longer, so you're actually writing more data than just writing this. So it's factors faster. And then if you can use compression, which we'll talk about in a bit, it's even faster. So, okay. Yeah. So, the question is about choosing the chunk shape. So there's no magic number. It really is machine dependent and in some sense, and it's data type dependent. So this is one of those things where you can fine tune the performance. Now, HDF5 or PyTables does a pretty good job of picking the optimal chunk shape for you, but you don't have to use that if you want to get better performance. And that performance is going to vary based on machine rate, like how big is your L1 cache, how much memory do you have. All those things go into what's your access time from disk. It really affects these numbers quite a bit. So, yeah. 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 If you're using a parallel file, well, everything's different in parallel file systems, but like, yeah, the chunk size of the file system is really important too. So, and the block size there. So, okay. Let's move on. For arrays and tables, arrays of all kinds and tables, except for VL arrays, the chunk shape is just set by this tuple of integers, right? So you can pass that as an argument to the constructor or this creation method. So here we're going to create a chunk shape that's 42 by 42. So say we wanted to have an array, a chunked array that is 4 by 4. We could have a chunk size that is 3 by 3, or we could have it 1 by 3, or 3 by 1, or 4 by 1, or whatever, as long as those numbers are smaller. So, but what you couldn't do is have a 12 by 12, right? You couldn't have a chunk shape that extends beyond the bounds of the array itself. Or you couldn't have a 12 by 12 by 12 because that really makes no sense. That's the point about the rank there. So, and as I've mentioned a couple times, you can tune this and it's great. So here's an example of this at work. I'm sorry if this is hard to read, but follow along on your own screen. So in memory, you're going to have this 2 by 2 array, right? In fact, it's going to be contiguous in memory, this 4 by 4 thing. In the file system, if you have it contiguous, right, if you have just one chunk, it's going to be laid out linearly, and it's not going to have any chunks. If you chunk it instead, you would end up with these tiles that each store their own chunks that each store their own part of the array. And these are n-dimensional chunks, as you saw. So you get one 3 by 3 up in the right corner. You get another one that just stores that little sliver along the right, another sliver for the bottom, and then the bottom right corner. And on the file, you would end up with 4 chunks, right? So store a 4 by 4 with 3 chunks, with a 3 by 3 chunk size. Only some of whose indices are actually valid at any time. Does that make sense? Okay, cool. All right, so note that chunking can be stored anywhere in the file, or the chunks themselves. I've mentioned this a couple times. They might, and then this B tree that HDF5 implements under the covers handles this mapping to and from what's on file, what's in the file system on the bottom, to what's in memory on the top. And you can note that they're based on HDF5's prediction mechanisms for chunks. There might be buffer space in between your actual data set. So you can, if you have a lot of chunks, or if you have chunks of like a particularly big size, you might end up with a non-trivial amount of white space in your file, depending on how you're writing that file and everything. Now you can typically squash that white space by doing a repack. So there's an H5 repack command line option. There's also a PT repack, a PyTables one, that'll go ahead and collapse that down. It also does some other things, like changing compression ratios and stuff like that. But there is, well, yeah, so it depends on what HDF5 decides is the right amount of white space. I've had this can get pretty ridiculous sometimes, because especially if you're working in a parallel mode, because it doesn't know, like it wants to be as safe as possible to not lose data, so it's gonna say, well, I think I'm gonna need like 5 extra chunks worth of space, so I'm, suddenly your file is like 5 times larger than the actual amount of data that you stored, because you wrote it out in such a way that it triggered this weird setup. So what you would do is immediately after that, you would just repack. And that's one of these parallel read-write implementation things. So just know that that is possible. And if it looks like you're getting your file sizes are extraordinarily large for no apparent reason, that's what's going on. And there's really no way to tell that that's what happened. There's no analytics for that, except for trying to repack and comparing the sizes of the files. So, yeah. HDF5 has great tools for analyzing what's in a data set and the metadata, but not such great tools for analyzing the hierarchy and the structure of the actual file overall. So, yeah. So that's a pretty bad chunk shape. Like this is not something you'd necessarily want to do. Typically you try to have your chunk shape be an integer division of the total shape. Yeah, that's what's best typically, because then you don't end up with this wasted space. But yeah. Okay. So let's talk about in-core versus out-of-core. So this is obvious, but calculations certainly depend on the memory layout of your data. Big surprise. So this is a big deal for your access time, right? You've got 16 months to wander around the world. So let's define these terms. There's some alternate terms that you can use, but using both of them simultaneously is confusing. So in-core operations are one that require all the data to be in memory. And so they're memory bound. You can think of this as the NumPy case. And then operations that are out of core are bound on, are CPU bound, right? So, or in kernel, that's where this gets confusing to talk about. And so that's sort of more of the HDF5 case. And you want to balance these so that both the CPU and getting things from disk or into memory are about equal. So suppose that we have this hypothetical situation. We've got two arrays and we want to compute a third array based on like some expression that we want to evaluate. So this creates three temporary arrays, right? So anyone want to shout out what the temporary arrays are? Everyone know what a temporary array is, or does? Yeah. Okay. Yep. Well. Yep. It's any of the binary operators. So the three are. Sorry, it's hard to see, but you get one for 42 times A, and then you get another one for 28 times B, and then you get another one for the sum of those two temporaries, and then finally you calculate the real array that you then output. So that's a lot of extra memory that you're using. It's one of these limitations of NumPy. So for n operations, you get n-1 binary or temporaries. But as expensive as that is, doing all of that from disk is even slower. So there's that issue. But the notion of chunks really helps here. So if you wanted to use less memory, this is sort of the classic way you would do it. Rather than having n-1 loops and n-1 temporaries, what you would do is you would just have one loop that indexes into all of these arrays, and you only get the one result array, and then you don't use excessive amounts of memory, right? So, but this would be really, really terrible if every time you were indexing, you were going to disk, right? That would be awful. And in fact, there's other problems here too, in that you would be casting back and forth to Python types to do this. That's a problem with NumPy as well if you were to write this in pure Python. So you waste a lot of extra memory and time doing that conversion back and forth. But it's even worse if you try to do this individually, right? Because every time you access an element, you would be getting the whole chunk and then throwing away all that data. So you'd be doing that all the time. Yeah, and then, so. No, so I is just the index into the array. This is a pure NumPy array thought experiment here. Yeah. But that hints to what is a better way to do it, which I think is on this slide or the next one. Suppose there was this virtual machine that you could feed arrays into, and then it would do this looping and chunking and splitting operation for you. Then you'd use a lot less memory, and you could operate on infinite length arrays, etc. because you would only do things every once. You'd only operate on the chunk individually. So recasting this previous slide, so this for loop that we all know and love, into a chunked version would look like this, where, say your chunk size is 256, you're going to now loop over the chunks and then do all of the operations on the chunks individually. You are creating temporaries, or here we're eliminating some of them, but you're going to create temporaries, but only of the size of that chunk, not of the full array. Do those operations and then store the value back into the appropriate chunk on your emitted array. So this is sort of the core idea behind a package called num expression. Who here has used num expression? Some of us? Okay. So num expression is an implementation of a virtual machine that for NumPy arrays does basically this, or it does effectively this. Like, it's a little more complicated. You give the expressions that look like Python expressions, but they're as strings, and then it'll go and chop things up. PyTables then takes num expression and combines this with the notion of HDF5 chunks and can iterate operations in a chunk-wise fashion in arrays on disk, and either output those directly to disk or read them into memory. So you can get these really, really fast chunked operations using num expression on PyTables, tables, or arrays, or whatnot. And the thing to note about this formulation is that this is really well suited to parallelism, right? Every chunk can be operated independently. You're reading in every chunk, and then you do these operations, and then you fan out and fan back in. So under the covers, num expression and PyTables use p threads to do these operations simultaneously, if you say to do it on some section of an array or the whole array. Okay. So since this is really low level, you don't have problems with the GIL or whatever. And to implement this, there's just an expert class in PyTables that is this VM that you get access to, and it's backed by num expression. And the guy who started PyTables is now the sort of lead maintainer and contributor to num expression, even though he's not really involved in PyTables anymore. And he didn't write num expression originally. So, sorry. Okay. Yeah, yeah, right. Well, Francis can have whatever he wants. So, I love that man. And this is really nice because the full array, especially when you've got terabytes and terabytes of data, it doesn't ever need to be read into memory to do complex operations on that array. So let's take a look at how this works. Here's just a simple example of an out-of-core operation. So say we've got 3 chunked arrays. They've each got their own defaults, right? So we're not even setting their values. We're just telling them what their defaults are. And then we have some out array. Sorry if this is hard to read again. That exists that has the same shape, right? The important thing here is that the shapes all have to match, just like in NumPy. But the chunk shapes can be different and whatnot. So we can hand a string expression of the thing that we want to compute. Here we're doing a times b plus c. We're setting the output array. This is so that we're not actually reading this into disk or reading this into memory. We're just doing the computation and storing the result of that computation back on disk. So like the array is never in memory. It's completely out of core. And then you evaluate that expression, and you can see that if you get the out, right, so basically this is for some multidimensional shape, this is going to be, what is it, 1 times 2 plus 3, so that would be 5. And if you looked into it, that's exactly what it would be. So, Um, SciPy objects? I don't think so. That would be awesome. You probably could, yeah. Yeah. I mean, assuming that your everything was like the valid symbols, yeah. So the thing to note here, there are some interesting scoping issues, or not issues, but points to be aware. So num expression by default has the scope of the, you can pass it in globals or locals if you want, and it'll evaluate there. And by default, it will take your current globals and locals scope and evaluate with that. So you don't have, you can specify the arrays in memory, and then you don't have to explicitly pass them to num expression, or num expr. Pi tables will do the same thing. You get local and globals if you don't pass in context that you want to execute in. However, it also takes the context of the file itself, right? So you can see that here. This is happening for sort of two reasons, but because A, B, and C are defined in memory. But if A, B, and C were just in the file, this would also work. If we didn't have these variable assignments, it takes the context of the file to execute in, which is nice. Yeah, you do have to do that. I believe so. So, yeah. Yeah? Well, I mean, the expression is different, but it's the same idea. Yeah. Yeah. So, well, I mean, this is going to happen. This was just an explanation of the algorithm. Yeah. Yeah. That's right. Yeah, that's what this expression is doing. So it's doing a single loop over the chunks based on the chunk size. Yeah, you could do it by yourself, but like if you wanted to use it in memory. But this is one of those things that Pi tables adds for you. Like, you don't have to create your own chunking algorithm. Like, yeah, that's right. Yeah.
So if there weren't all at root, would you have to say like import variable on there?
I'd have to look into it. So it's in the doc somewhere. Yeah. If you'd have to pass. You might have to pass it in the context of that group somehow. So yeah. In your
You mentioned that it was using features behind the scenes to realize what else you remember.
yeah.
Is there a way to set how many vector or automatically take all of one or?
You can set them, or it will automatically take all of them. So num expression has an API for setting them. Pi tables also has an API for setting them. So, yeah. Yeah. Yes, that's right. Yeah. It's its own like virtual machine and language, right? So, yeah.
If A is not a chunk array and is a regular NumPy array that have
Yeah.
really many elements, would it fail to?
No. So you can, it will seamlessly mix in-memory NumPy arrays and arrays on disk.
It will only have to match the shape.
Yeah, only the shape has to match. Yeah. Okay. Yep. Yeah, you could. So you can create anonymous, like unnamed arrays here, and then you just have to give it a name in memory, and then num expression would take that name in memory and use it, but it wouldn't have a name on disk. In this example, so this call creates an array on disk. And actually, it doesn't even fill it with values. It's just the metadata associated with that array. And that's always true. And then you get a reference to that point or to that HDF5 object. And then that's what A is as computed in the num expression, or in this expression here.
So TP.expr, that's taking the data into the cache.
Which cache are you talking about?
Well, the L1
Oh yeah, so yeah, that's right. It's bringing data into the L1 or L2 cache or memory. Yeah, that's right. Yeah.
Is there an API for routing the expert class to like a custom object that say some spec method that make data frames?
I'm not a num expert, but I don't think so. Yeah. It's not particularly, my understanding is that it's not super difficult to add new functions to num expert, but it's definitely something that happens within the context of num expression development, not something that you would kind of wrap around. So you could, the code for this in PyTables is basically, it's one file of around 500 lines. It's not super hard if you wanted to play around with it. Like it could probably be done in something like for pandas objects or whatever relatively easily. But I don't know the details there. So I don't think it would be super difficult. Okay. Yeah.
Does HDF5 have any integration with
No. So yeah, so the question was, does H5Py have integration with NumExpert? And the answer is no. This is one of those features that's a PyTables thing. You can use NumExpert with H5Py, but it doesn't have any special. It won't be chunk aware per se, so it would try to read the whole array into memory, I believe. So, and that's the thing that gets done here automatically. Is that like PyTables will go read the chunk shape of your array and then use that as the chunk shape that NumExpert knows about. So, okay, cool. So this is super useful in the context of querying data from your data sets. So if you have some existing data and you only want to read in things that satisfy some expression, Boolean expression, you can do that, and it will all be parallelized, and it uses this num expression tooling under the covers. So this is very similar to using with the where clause in SQL, which some of you know about, or the where method in NumPy. So there's a few different ways to access this kind of this querying capability. So and they all live on the table class. You cannot index, you cannot query arrays or chunked arrays. You have to do that using the normal NumPy semantics. If you want to use these, they live on the table. And inside the table, they also get the context of the table. So the column names become variables that you can use in your conditional expressions. So the where one is the simplest. You just pass a string of your condition statement that you want to query on, and that returns that's a generator. So you just use it in a for loop like you always do. If you want to read that back in as a list, there's this get where list method, which takes the same. If you want to only read in, if you want to read that into its appropriate flavor, you would use the read where rather than querying and then looping. And then this is backwards actually. This is one of the things that changed. This is actually an append where, and what that does is on the table that you're on, you're going to query based on the condition and then append those results to another table. So that's really useful if you want to do the sort of thing that we talked about with these masks or whatever, and you want to do that automatically and never get the data in memory. So that's another mechanism. Okay. It's actually copying data on disk. So the linking in HDF5 is two data sets. Like you typically don't link to elements of an array. You link to the array itself. Okay. Although the links themselves can be in data sets, not in PyTables, I don't think, but in HDF5 itself, you can have a data type that is a link to another data set. And it'll resolve those automatically when you go to access data. It's typically just easier to, in that case, sorry, this is getting off in the weeds, but in that case, it's easier to just use a variable length data set than to use a link to another data set. It's also possible to link across files, which is interesting and exciting, but I wouldn't recommend it. So there's lots of wacky advanced features that they probably shouldn't have done. The where expressions have to return Boolean values as you would expect, right? Whether that's included in the true false and whether that's included in the result. Executed in the context of globals and locals, like I mentioned. In the simplest case, here's exactly what you would do. You get the context of the table, so say you have column 1 and column 2. You want to check, or you want to get every row where column 1 is less than 42 and column 2 equals column 3. And that just happens nicely. So for a speed comparison, just very briefly, if you were to do this without using num expression, this is kind of what it would look like, right? You'd have this list comprehension where, say we just want to pull out the element of column 2 for some complex expression where we read in every row or we're reading in all the rows. That's how it would look. And to refactor that to use num expression, you basically just add a where call and make that whole thing a string and remove the row indexing. It's pretty easy. So it's it's easy to refactor, or it should be easy to refactor. Note that it uses the bitwise operators rather than the and and or, although there may be yeah. No. Yeah. There isn't. So, I mean, that would be fine, but even if that was a num expression, I'm not sure that would propagate up to PyTables soon. It might, but no, I've never seen anyone talk about that. So, yeah. Hmm? So what does the num expression? The where call. Oh, we'll get to that in a moment. Yeah. Here, in fact. So there you go. So this is that complex query that I was mentioning on a table that has 10 million rows. This is important because it fits in memory. We haven't talked about compression, but here's a bunch of different data sets. This is something that Frances put together a while back. So it's probably a little out of date, but in terms of modern computers. So you want the numbers to be lower here, obviously. If you just have, this is for something that was one whole major release ago. Oh, no, sorry, you want the numbers to be higher. So, right, God, these flip back and forth a few times. So if you use the original mechanism, that's about, and you're doing this just with a list comprehension, that's about 10 times as slow as using the where in num expression. So it's about a factor of 10 for this data set. No, so you're going to get, when you write the where statement, you get these implicit temporaries that are the size of the chunk. But that's all handled by num expression. So you're not getting a full array, you're just getting whatever the chunk size is. You have smaller temporary variables that are the size of the chunk, rather than if you had an array with 10 million rows, right? You might have a chunk size that's, I don't know, 1,000 or 10,000 or something. And so getting temporaries that are a few orders of magnitude smaller than the total size, and you're doing this in parallel, is going to be much faster. Yeah, well, so in normal Python, you get temporaries anyways, right? Like if you just had the expression a times b plus c, yeah. So you get those temporaries too. It's exactly the same. It's just that you're minimizing the size of the temporaries while balancing that concern with this access time. That's really the trick, is trying to balance, like, making the processor do as much work as possible while waiting to get data from disk. So, okay. So it's about a factor of 10 faster. Yeah, so this one is better. And then if you add compression, it takes a little longer because you have to decompress. And then if your data is so large that it doesn't fit in memory, depending on your compression you use, it's, again, factors of 5 to 8 faster to do this to do the where query. Regular is when you're just doing the raw list comprehension, the version that I showed. So you can do this, and it won't fit into memory, right? Because you're only going to be pulling a chunk at a time. Like when you iterate over a table, you only pull out the chunk that you need based on where you are in that iteration. You don't pull out the full. Yeah. So all I/O happens on chunks. Yeah, you can. Yeah. That's right. Yeah. So, and that code is kind of ugly, but under the covers. But you're basically the generator expression will it creates you this iterable, and then that iterable object stores where you are and has a cache for the chunk that you're currently on. And so the next time you go to the next chunk, it'll pull that chunk out and then continue on its merry way and forget about the current chunk. So, yeah. In this expression, so there's a lot of stuff there. So no, you don't get a fork in the process. It's p-threaded. The function will be available as a variable, but you couldn't call that function, right? Like it's still in the namespace, so you could access it, but you couldn't do anything meaningful with it. So num expression defines certain ufuncs that it knows about. Most of which are shape preserving, and there's only a couple of reduction operators, so like sum is now supported and things like that. But yeah, so num expression is relatively restricted in the kinds of operations that you are able to do in it to the kinds of operations you're able to do with arrays natively. Well, so for this like 1 billion rows case that doesn't fit into memory, you just couldn't do it. And then this is where depending on the number of processes you have and how many you say to use with pthreads, you do get a performance benefit because you're doing those, like it's roughly the same speed. They're basically equivalent, but you've got it chunked up, so you're doing it in parallel, and that's where you get a performance benefit, rather than doing it in NumPy. And you can do that with num expression. You can say like, passes off to num expression and index in this way. Just a normal using normal NumPy and normal num expression, you can test that it's faster to do it that way. So, yeah, it's not hard. Okay, all right. So now we have an exercise. So I know that was a fairly long stretch. So here's this is probably the most complicated exercise of the tutorial. So this one is called Chrono. And let's go ahead and look at it. Oops, God, I don't know how to do anything. Max. Okay, so your friend Chrono has been murdered by the mighty Lavos. Luckily, you have a time machine, so you can save Chrono. Unfortunately, you're not sure when Chrono died, so you have to go through the ship's logs to figure out where Chrono is. Okay, so step one is to search through the ship's logs and print all of the times that Chrono was alive. Step two is to figure out if you ever left Chrono alone, and if so, when. Write out these times to a separate table with, that should be without fully reading the log into memory. Send 3 friends into the fray to help Chrono. And then 4, who are Chrono's best friends, who are his worst, and judge that by the amount of time they spend with him. Okay, so if you were alive in 1996, then you get all of these references. And had a Super Nintendo, so I should mention. Okay, so there's a log file, an HDF5 file that'll be created for you. You're going to open that and then have at by searching through the array, or searching through the table, excuse me. You might want to figure out what the D type is or inspect the columns of that table. They should make sense. And then do some of these operations using the num expression and querying tricks that we just learned about. So, and of course, close the file. And why don't we give 10 or 15 minutes for this one? So if you get stuck, please raise your hand. So, this is another way that IPython is really nice to use because you can, as Nathan discovered earlier, there's a calls attribute on the table, and you can use that to just tab and find out what the column names are. So. No, so you create it. Just if you execute this first cell, it's going to create the data file. You could also cheat and look in that file that we're importing. Or cheat by looking at the solution. like this Twitter battle that's going on right now. Anyone stuck? Yes. Fair. You can only do a copy. You don't want to do a copy, you do an untitled view. And you can have some other errors and you can match it and just say yeah, you should check the answer. Yes. And that actually really does the view is a little bit reshape will do a copy if you do array.shape equal, then you yeah. Let's give it a couple more minutes. People are clamoring for more. Are there other characters in the game? He floated, that's why. Yeah. Any, anyone, how many people are finished? You guys should work on these exercises in the next report. Should remember my password. All right, let's go ahead and go over the exercise since we're kind of in the home stretch here. So if we look at the solution, and feel free to continue this on your own later. Whoops. Okay. All right. So if we just wanted to read the times where Chrono was alive, what we can do is, since the Chrono field is since these are Boolean fields, you can just use the expression Chrono, and go ahead and access, or sorry, no, that's the, yeah, so you would use the field Chrono on the log table and grab all of the data there. So, and then grab the timestamp field. So that's the simplest way to read in the contents of one part of a table based on the expression, based on another expression. And then you get this big array of times. So, okay. Any questions there? It's just this read method. It's pretty easy. There are a bunch of other ways you could have done that. That's just the most concise. If you wanted to create a new table where Chrono was alone, you would use the same description from before, and you would create a condition based on the names of the friends, right? So we're just doing some string manipulation to say, it's kind of hard to see, but this is a tilde, so you would do not where the friends are and where Chrono is. You create that expression programmatically, and then append that result to this Chrono alone table, as you see there. And then if the length of that table is greater than 0, then you know that Chrono is at some point less than 0. People understand what's going on here? This is this notion of programmatically creating these num expressions is pretty useful. Okay. Then, if you want to send in 3 friends, you can just index where Chrono was alone for those into those points, and for those rows, set them equal to true. Update the row, and then flush everything at the end of the day, and then that will rewrite those elements of those rows only. Okay. You could have created a mask and done it that way, but this is sort of the in-memory mechanism for doing so. If you wanted to find out which friends are Chrono's best friends, you could do it this way as well, where you, for every friend, you would go ahead and compute when they existed together, and then sum up the length, and then the best friend would be the one with the maximum, and the worst friend would be the one with the minimum. So, and then iterate that way. Everyone understand? Cool. You guys are pros. All right, so before we go on, I don't know who, there's a little battle on Twitter right now that I wanted to bring up about the safety is part of performance. I don't know who Glenn Carlson is, but if they're in this room, that would be cool. We could talk more directly. It's a. Oh, okay, okay, that's hilarious. Is Jeff? Oh yeah, Jeff Terry is not in this room either, right? So when done proper, I just wanted to bring this up. So when done properly, safety doesn't impair anything. When done stupidly, everything grounds to a halt. So I agree in principle, but that's not, so in the context of HDF5 and this like white space issue, and the safety around that, I should note that it's not possible to do the kind of things that HDF5 wants to do in what is meant by safety here, in a sane amount of time. So when you're trying to write out like a petabyte or an exabyte of data on 100,000 processors, it would be time prohibitive to go to every processor and ask which chunk it has in serial and then write them out. You have to write them out in parallel for that process, for that job to be done in anything that's respectable. So, I mean, the safety comes from the fact that you get this extra white space, which can be annoying, but not from the fact that you're not checking with every other processor. So just to note that. In case you weren't aware of this nuclear engineering safety battle that apparently was happening. Yeah. Thanks, Katie. Who's a rocket scientist, apparently. And never the two shall meet. Okay, so let's go on. We've got about a half an hour left. So we might skip a little on some of the exercises or go very quickly with the remaining ones to get through the rest of the material. The next really important thing I want to talk about is compression. So another way to address this starving CPU problem that isn't just about chunks and doing data in parallel with reads is compressing the data as it goes out to disk and decompressing it as it comes in from disk. The compression for HDF5 happens on this read-write, and like with everything, compression happens on chunks. So every chunk is compressed individually, right? So you get your own pattern table for every chunk. So that's important to note because that means that there's some overhead even on disk with compressing. As people know, if they've done a lot of work sometimes for very small data, when you compress it, it can end up being larger, and that's really annoying, so you have all those same problems here. And each chunk is compressed independently, like I mentioned, so every chunk ends up with a varying number of bytes. almost all the time, this is the very number of bytes is less than the original chunk size. Something to note is that a limitation of HDF5 is that because the compressed version you don't know the size of, currently you cannot compress a parallel read and write. So like if you're using MPI with HDF5 to read and write data, that cannot be compressed. That it's been floated that they should implement that because it's a really smart thing to do, but it's a little tricky on the implementation detail. It's not super tricky. It's not actually that hard. They just haven't, there's no account that they can bill to get that work done. So, although it'd be really useful. So note that that's another limitation. Not a big deal for PyTables because PyTables doesn't assert an MPI dependency ever anyways. But if you're going to use H5Py or HDF5 itself, note that. Yeah, has some storage overhead, but for like really regular data, it's great. If you've got tons of zeros and you don't really want to worry about storing things sparsely, this is the way to go. It will just collapse everything down. Okay. And, oops, I should mention, it's also faster, right? Because of this starving CPU problem. In general, compressing your data is faster than not compressing it. So it's more CPU intensive, but since you're waiting around to go back and forth to disk, you actually get some performance benefit. Just because you're transferring fewer bytes across that memory hard drive boundary. And you make the processor do more work. So, okay. This is really nice because compression is guaranteed to be part of HDF5 always. HDF5 itself requires zlib. So you're, at minimum, you're going to have zlib compression available to you. There's a plug-in architecture in HDF5 such that you can define your own what they call filters, of which compression is one. A filter is basically it's a step in a pipeline for reading and writing, and so you can add other compression algorithms. There's a few that HDF5 supports natively, but it only requires zlib. So you can write your own compression algorithms and apply them to your data in HDF5 if you want to. It's not any harder than anything else in the C API. So that caveat. Oops. Oh man, I've got some rest in here. You'll forgive me. So zlib is always going to be there. LZO is supported natively by HDF5. bzip is also supported natively. They have their own performance characteristics, of course. And BLASK, which is one that is a compression algorithm that was written for PyTables originally, specifically to apply to table-like data. And so for these kinds of operations, BLASK like blows it out of the water. BLASK is now its own library that you can pip install or whatever, however you want to install it, and you can use it on normal files and other things. There's like BLASK arrays in memory that are compressed in memory and things like that. It's pretty cool. But originally it came from this use case, and it does really, really well here. zlib in general is going to be the fastest, but it's also going to compress sort of not as much. It's kind of your de facto compression. So if you want to use a filter in HDF5, or if you want to use compression, you create an instance of this filters class, and it has a bunch of keyword arguments in its constructor, two of which relate to compression, notably the comp level. So this is a number that ranges from 0 to 9, like all compression, and which compression mechanism you want to use. So if you get PyTables, you're going to get BLASK. But if you want to be ultimately portable, you probably shouldn't use BLASK. You should probably just use zlib or one of these other ones. The filters you can apply to any You can apply to a file, you can apply to a group, or you can apply to a data set, and all of those can be different. In Pi tables, filters cascade down the hierarchy. So if you set it on the file, if you set filters on the file, it's going to apply to everything. You can then reset other filters farther down the hierarchy if you want to change specific ones, but by default, it's just going to parallel, or it's going to flow down. If you set it on a directory, it's going to, or on a group, it's going to apply to all the data sets in that directory. That is not true for HDF5. You have to construct the filters per data set in HDF5. So that's a key difference to note. You can apply, if you want to set them on a data set specifically or on a group, there's this semi-private but part of the public API _v _filters thing that you can set on the group or whatever. So the reason why PyTables has a lot of these attributes that start with underscore, and the reason for that is so that you enable natural naming, because you don't want your PyTable specific attributes to conflict with things in your attributes, the attribute names that you get from your groups or your arrays or your table names. So well, yeah. So it would be pretty annoying. Like, you might need to go into the class dict or whatever. It would be bad. But like, no one in their right mind would have this name as a array name, theoretically. Right. Yeah. That's true. Yeah. The metadata is stored in the file. So like, when you read a file, it will know what filters are applied to all of the data sets in that file. Yeah. Yeah, that's a good thing to note. And of course, like always and ever, filters only apply to chunked. They apply per chunk. Okay. So there's some tips for choosing compression parameters. You almost never ever need to go up to 9, and actually that just wastes time. So your speed ups tend to get lower. 5 is pretty good for almost everything I've ever done. And in fact, in most cases, 1 is sufficient. If you've got data with a lot of the same value, like it's sparse and you've got a lot of zeros, setting a compression level of 1 will do 90 or 95% of the work for you, and it's going to be way faster than anything else. So do a parameter sweep of the 10 compression values or whatever, and just figure out which value you should pick. It's really quick and easy to do based on whatever data format you have. If you need to guarantee portability, especially to other HDF5 based applications, then use zlib. If you don't care, use BLASK. It really is optimized for HDF5, as we'll show you. And I'm not really going to go into BLASK too much here, but so here's some speed up statistics. So here is just for zlib at different compression levels. Like this really shows the level 1 is good enough for almost all cases. So you've got this very number of rows, and at no compression, you've got your blue curve way up at the top, and then your other curves are just down there at the bottom. And there's some difference between them, especially with large number of rows per chunk, but it's not a significant difference for most cases. So, okay. Data's great. Here's a comparison of different automatic or different compression mechanisms. So, and their various levels. These are all at level 5, and then our automatic chunk size is listed right here. So, if you have no compression, it's this is throughput. So, like that, right? So you've got in megabytes per second, not rows. So, or yeah, I wonder how to read this. Yeah, so in megabytes per second. So you can see that BLASK is just going to get you much more data than it's going to get closer to the uncompressed version in terms of its speed characteristics versus something like zlib, which is a lot lower throughput, but is guaranteed to be everywhere. So another example is for different, this goes by size based on the chunk size for a large array. And again, you can just see that no compression is just very different from the effect of using compression whatsoever, any compression mechanism. That was all write speeds. This is read speeds. On the read side of things, your uncompressed version, as you would expect, based on what we know about the starving CPU problem, is going to be the lowest read speed, and then as you read compressed data based on whichever algorithm, you're going to get faster, and BLOS in general just blows the other compression mechanisms out of the water. So. So I don't know. I don't think so, because it typically looks at the size of your it looks at the size of your data type, and it looks at the size of the array that you're making, and it figures out, like, it's not the simplest algorithm, but it's not super complex, and it's going to be in that neighborhood. Like, note that this isn't on the peak of any of these. It's like something off of the peak, which is why you can fine tune it. But it's gonna get in the general area, and I've never seen it do something terrible where it just like really mispredicts the chunk size wildly to something that's much smaller than cache size or much larger than cache size. So, because it's a really easy thing to figure out, like how much RAM do I have? So, yeah. We can go through the algorithm later if you're that interested, but I've never seen it dramatically fail. Okay, so here's the mean read time. This is, again, you get some performance benefits for, in certain cases, although there's a crossover point between where the compression really is buying you something where it's not. So, okay, so what's our time here? Why don't we, do we want to do this? Why don't we spend 5 minutes doing the spam filter exercise? So I'll just go over this very quickly. And then we'll probably skip the last one in favor of time. So why don't we just try to do steps 1 or 2? Email is terrible, as we all know. And a lot of it's junk, so create an HDF5 file, uncompressed, close the file, and use the getSize function to get the size on disk. So PyTables and HDF5 provide utilities for figuring out how large these things are that you can investigate with the API. And then do that, but with zlib compression at level 1. So if we could just do those 2 steps, that would be awesome. So, and then here's some data that you can use. And note that I didn't open a file for you this time, so you have to do that yourself. Oh, sorry, the getSize function comes from os.path, although there are mechanisms for getting the size of the array on disk as well, on the table class and things. So let's do 5 minutes for that. All right, so let's go ahead and go over this just really quickly, the first two here, since that's all I asked you to do. So in the first one, all we're going to do is we're going to go ahead and open a file, and well, here I added some timing information just to make it nice, and create an array. And giving it an expected rows hint, although you don't have to do that. That expected rows hint really helps pick the proper chunk shape if that's what you're interested in. And then you can use the get size to get the size of the file. So in the uncompressed version, we have this number of bytes, and it took 54 milliseconds to write. Taking that exact same thing, but instead adding a zlib filter at compression level 1 will give it about a quarter of the size, it looks like, or a little less. And took somewhat longer to write on my machine. So, okay. Yeah, so in pi tables, you need to have it be explicitly a chunked array or an E array or a table, right? Like pi tables needs to know that it's chunked. It doesn't want to, even though it's chunked up under the covers, like it won't, it assumes when you create an array, you want a contiguous block of memory that you can, that is unfiltered by that. So does that, yeah. You have to use it in a chunk mechanism in pi tables. So, yeah. Yep. So tables are automatically chunked. If you want to create a chunked array, it's just create C array. And if you want to create an extendable array, the extensibility comes from chunking. So if you want to create a extensible array, it's already chunked, and you just use E array. So tables are extensible, yeah, and they're chunked and everything. Tables basically have every feature you could possibly imagine, and the features get taken away with these other data structures. So convenience, yeah. So this is really to show the properties of compression, not show the properties of like creating a complex data structure with named fields and things. So, okay. Any questions? All right. So let's go ahead and continue on. We only have a few minutes left. Try to get you out of here on time. So one thing that you can do is you can persist and depersist other Python data structures into HDF5, like we saw this with lists. That's kind of the obvious case. But if you can get something into a list and want to declare an atom type, or you can get something into a NumPy array, then you can persist and depersist it pretty normally. And there's been some talk about doing this more automatically, but there's nothing really there. This got back to someone's question from earlier in the day. So lists and tuples are easy, as are arrays. Things like sets and dictionaries are a little trickier, but you can do it pretty easily. So let's just take a quick example of sets, serializing and deserializing sets. So here you have a set. You can just toss it into a list comprehension right there in line, and then you would persist this as a list. Or it'd be persisted as a list. And then when you wanted to read it back out, it's really easy to just call the set constructor around that data type, and you get a set back as well. I mean, maybe this is normal and obvious, but the key thing to note is that you have to declare the data type here. Okay, so there's an exercise which we will skip. Well, why don't we can look at it, and then you can do it at home. Since there's the solutions, I don't feel so bad. But the idea is to do basically the same thing, but with a dictionary rather than a set. And so you've got a file and you've got a dictionary with some data in it, and how are you going to store that as on disk? Anyone just want to, by word of mouth, take a stab at what you would do? Yep. And as what? Yeah, so you could do it that way, basically make a structured array out of them. That's probably how I would do it. So you'd have a keys column and a values column. You could store them separately, too. You could have 2 different data sets and store them as individual one-dimensional arrays. But you have to add the data types. That's sort of the key point of this. Okay. Awesome. And let's see. So we won't go into the exercise. There's a lot of stuff that we missed that we didn't get into in the time that the tutorial took. We didn't talk about how you walk down nodes. It's pretty easy. There's a walk function, method that you can filter on the kind of node that you're iterating over as you walk, which is awesome. We mentioned file nodes, which are basically an infinite character array that implement the Python file interface, so you can use them exactly like a file. We didn't talk about indexing. It's there, so if you have tables, you can, in a very relational database-y kind of way, there's a way to create indexes into that table, and that can speed up your queries, and that's pretty awesome, etc. And if you change the data, it'll know that, and it'll declare it dirty, and you can reindex, etc. That's all there. We didn't talk about how to migrate from SQL or CSV or anything, but these days it's particularly easy with pandas, so that's how I would go about it. Just load in the data into pandas and then output in HDF5. HDF5 is just a block of data, so you could store it in. I've known people to store HDF5 files in SQL and MongoDB and things like that, so that's not unheard of. You can also do it the other way around. I do a lot of storing JSON files in HDF5 arrays, which is pretty fun. It's hard to index on them, but whatever. And there's this HDF fuse thing that you can use if you really want it as a file system as well. Okay, so last couple of notes. I'd like to thank the HDF group for writing this awesome piece of software. The PyTables developers have been great, and we've really come a long way, I feel like. NumPy developers, of course, H5Py, because we share a lot of code back and forth. It's another great project, and of course, we're always looking for more developers who are interested in the Pythonic version of the Pythonic interface to HDF5. And with that, I'll take any questions. I'll also hang out afterwards if you want to talk to me about individual problems or things that, or projects that you're working on. I love to talk about this stuff. So with that, thank you very much and enjoy the rest of SciPy. So yeah, have a good one.